Right now, I work at a company called AdRoll. So AdRoll is an advertising company. You probably haven't heard us, but you've definitely seen our work. We bid on all of those little ads that you see on web pages, unless you're running an ad blocker. So the advertising industry has changed. So it used to be that you would take a big chunk of money and you would hand it to an agency. And these agency people would think real hard, and they would make something that was relatively banal, and then it would sell a lot in the Midwest. So advertising is now less this, where you hand over a giant chunk of money to people, and it's more this, where you hand over small chunks of money to mathematicians and computer scientists, and then they figure out how to manipulate people using their own data to buy your stuff. So engineering plus mathematics equals ads. You're welcome. Everybody loves ads on the internet. So I work on a product in particular called it's a problem domain called real-time bidding. It's a pretty interesting problem domain. So it's low latency. So when you go to one of these web pages, you've got basically a tenth of a second before the human eye notices that you've gone from completely blank space to ad space. So you've got less than a tenth of a second to say to the exchange, I will pay this amount of money to show this ad for roller skates to this user. That means that your computer system has to make these sophisticated decisions about how much money to pay. It's a firm real-time system. So for those of you that know real-time systems, a soft real-time system is one in which you go past the post and your computation still has value. A hard real-time system is one in which you go past the post and things catch fire and people die. A firm real-time system is one in which you go past the post, nothing catastrophic happens, but your computation has no value. If we take 10 minutes to say to the exchange, by the way, $5, they don't care. We've gone past the deadline. In our system, at our scale, we're highly concurrent. We do basically 2 million transactions a second at peak. This is actually higher now that it's Thanksgiving and Christmas, and I honestly have no idea what it is at the moment because I'm on vacation. But we do about 90 billion transactions a day, spread all around the globe. And we're global, 24/7. So real-time bidding is really, really similar to high-frequency trading, except we have an auction deadline and we don't shut down at the end of the market day, because the market day doesn't stop. So in short, I build complex systems. They have these interesting features. They have nonlinear feedback, so the errors that manifest in a complex system feed back into itself and cause even worse problems. They're tightly coupled to the external systems. So if the external system has a fault, you actually have to handle it, or you risk failing terribly. And they're difficult to model, and they're difficult to understand. So you might think that because you've put this thing together, you actually understand it, but you don't understand it because you have this feedback loop with this system that you don't control driving you crazy. Also, you have this feedback loop with other people in your team who you don't control, but that's another issue. Complex systems and complex organizations are an interesting field of study. Bad things happen when complex systems fail. So generally you've built one of these things because you have some sort of systemic problem or systemic interest. And when you have successfully put one together, you've taken all of the simple problems, the ones where you stub your toe on the edge of a coffee table, and you turned it into something where you blow your foot off with a shotgun, just because you've solved all of the easy things. So the things that go wrong are really wrong. Carlos Bueno, who works for Facebook, wrote a really great book called The Mature Optimization Handbook. And he's mostly talking about when you would figure out when you would try to choose how to optimize the performance of a system. But he has this thing in it where he says that humans are bad at predicting the performance of complex systems. Our ability to create large and complex systems fools us into believing that we're entitled to understand them. So substitute performance for just basic behavior. And it's a really, really interesting insight. Just because we can knock something together does not mean that we can understand it, and it does not mean that we can maintain it. And like I said, complex systems often create worse problems than those that they solve. So in case you don't notice, or in case you don't recognize this photograph, these are heavily irradiated Soviet military vehicles after the Chernobyl cleanup. You have a reactor, it makes electricity, it blows up, and now you irradiate a good chunk of the Ukraine. Whoops. So the key challenge to sustaining a complex system is to maintain our understanding of it, which is sort of a pessimistic thing. You know, you've knocked this thing together, and now you're sort of trapped by it in trying to maintain it. So what can we actually do to maintain our understanding of it? So there's a lot of currents of thought. One current of thought is to have compile time guarantees. So you have compilers that give sophisticated warnings, variables that get unused. If you study Rust at all, they push that really far where they say, well, this memory access moves into this new memory access area, so you can't use it anymore. And those are great. They solve a certain class of problem. But they don't solve all problems. Even though you can't scrimp on them, compile time guarantees are not sufficient to make a completely safe complex system, or even a simple system. Ahead of time verification, so these are things like testing or quality assurance, ahead of time being ahead of the time where you put it into production and people rely on it. These are also not sufficient. You know, your test cases can have holes in it because in your hubris you might have decided that you can understand all of the edge cases in the system, but you can't. You simply can't think of everything. Your quality assurance people also simply can't think of everything. So even though this is not sufficient, don't scrimp on these either. You know, compile time guarantees and ahead of time verification, super, super valuable. But to actually maintain our understanding, what we need is insight into the running system. We have to understand the system on its terms. I mean, we have to be able to interact with it as it is proceeding. So with regard to building airline systems, which is my primary professional focus, what do we look for? So all the time people say, what should we look for in a system? So look for the VM killers. So any of you who have any experience with Erlang have probably allocated 2.2 million atoms and then gone tee-hee as the node crashed. This is actually a problem in some production systems if you dynamically create atoms. So check for that. ETS table limit, process count, limits, something like 130 million, which can happen if you've got enough RAM, ports limits. All of these limits kill your VM, so you need to look out for them. Application performance regressions, so these are squarely in your domain. These are things where you've done goofed, and your system has gotten too slow to actually service all the traffic that you're now sending it. Abnormal application behavior, so you might have perfect performance, but your application might be doing things that you didn't expect, or that are bad for the user. And it might not necessarily be enough to violate the contract that you have with your user, but it's not good behavior. And you also want to look out for surprises. So this is a sort of catch-all category, but surprises are bad. You want systematic, boring behavior in an important system. It should bore you to tears, and if it bores you to tears, it is doing its job. Instrumentation is how we sort of get this insight into the running system. So the great thing about working in Erlang is the bean was put together by very practical people, so it's just studded full of information that you can use to understand how the VM and your application is running, or your system is running. So there are 3 primary functions that are available in the standard library, all in the Erlang module that you need to know about. Erlang memory 1 and Erlang memory 0. 0 just gives you a giant dump. Memory 1 is the interesting one because not all of memory 0 is super valuable. The things that you particularly need to feed into memory are ETS, which gives you the memory allocation of ETS tables. Binary, you know, all of, I'm sure you can guess what all of these do. Atom is, you never really, since atoms are system integers, they never really allocate a lot of memory, but if you get too close to the limit, it's a real problem. So Airline Statistics. This is another one where 0 pumps out an incredible amount of information and not all of it is valuable or understandable on an automated fashion. So the 3 things that you particularly need to look out for with Statistics 1 are run queue. Run queue gives you a measure of the processes that are waiting to be executed by scheduler threads. So it gives you basically a count of how backed up your system is. If you look at a completely idle Erlang VM, statistics run queue 1, well, I bungled that, but I'm not a compiler, will give you 0. There's nothing waiting. If you have a very loaded system where latency jitter is very high, I guarantee you'll have a very high run queue. Garbage collection, how much garbage is your system allocated and then destroying? Often it's not a problem, but if you are destroying gigabytes of stuff a second and you don't intend to be, that's something you need to look into. I/O is another one of those things where maybe it's a problem, or maybe it's not, but you need to watch it, because as soon as it starts to spike, you actually have a problem. And the last one is Erlang system info. Erlang system info is pretty incredible in that it tells you almost everything else you need to know about the system to make sure that it's still running. Two things to feed into it are port count, because you have a hard limit on the number of ports, and process count. Process count is only interesting not because there is a hard limit, although there is kind of one, but because it's so easy to make processes, sometimes you'll make millions of processes you didn't intend to make. And then there are a lot of underscore limit arguments that can be fed into system info, which is valuable because you want to make sure that you don't get near the hard cap limit there. So port count limit, process limit, things like that. So these are all VM, and the VM is not the whole story. Like the VM is the basic understanding. The VM is the road underneath the tipped over Jeep, I suppose. But what about our own work? How do we track abnormal application behavior, performance regressions in our own applications? There are a lot of libraries for doing this, and some are better, and there's one that I like quite a lot. It's called Exometer. So Exometer is a really, really fantastic library, but it has sort of a complex understanding of how you measure things, and it's important to understand Exometer on its own terms. So a metric is just a measurement. This could be CPU at a certain moment. It could be the latency of a certain request. It is just a value in time. An entry is a receiver and an aggregator of metrics. So this could be a histogram. So you take, say, the latency of a request and you start to put it in a histogram. So you can build a histogram of the latency of requests. A reporter is something that periodically samples entries, so it periodically looks at the histogram and then ships them to another system. So if you have, say, a remote monitoring tool, it periodically takes a snapshot of that histogram and ships it over the network so you can learn on it. And a subscription is the definition of the regular interval that a reporter goes to the entry. So a subscription for, say, the stats_d reporter of 15 seconds means that every 15 seconds, the reporter will go out, look at the histogram, ship it across the network, and then you have a monitoring tool and an alerting tool to do all of the important work on the other side. So Exometer is fantastic because the upstream is incredibly responsive. I honestly don't know if Wolfviger ever sleeps, because I know I email him in my day, which is 9 hours in the past, and he's still up and doing things. Metric collection, aggregation, and reporting are decoupled. So this ends up being hugely important if you ever want to send any of these in opposite directions. I think I moved out of the mic. In directions that vary. So if you have a histogram that needs to go to 3 places, you don't need 3 histograms, you just need 3 reporters and 3 subscriptions. There's static configuration, so if you know there are certain metrics that you're going to use, you can have them reflected in the configuration. But if you decide at runtime, whoops, I goofed, and I need new things, you can create them. Or if you're going to dynamically create metrics, you can also do that. And at that role, we do a combination of both because it can be incredibly cumbersome to have almost 1,000 metrics statically declared. And it has very low, very predictable runtime overhead. So this gets back to your system should be incredibly boring. Exometer is incredibly boring once you've got it all set up. It basically does exactly what it should do, and you never think of it again. So defining entries. So this is the static configuration. So if you, hopefully you can see that. Yeah. So if you'll recall, I discussed Erlang Memory 1, and the interesting thing here is Exometer has the ability to invoke a function as an entry and pull the value out of it. So in particular here, I'm going to have Exometer call Erlang memory with the values ets and binary, and then it'll pull the value out of that. So Exometer now has an understanding of what the Erlang memory return is on a regular polling period. Erlang GC, which is a function that I didn't discuss earlier, or Airline Statistics, excuse me, is a function that I did discuss earlier, and it's called Erlang GC. Exometer has this match facility, so if a function returns a complex tuple or a record, Exometer can pull that apart for you. So you see that down below. where total call, or total collected and received word, and then the third argument we don't care about. So now Exometer has an understanding of garbage collection statistics. And Exometer has various types. There's a simple counter, which is just a monotonically increasing counter, but there are spirals. So if you have, as I do, say 1 million metrics going into something, you don't want to keep aggregating that in memory. A spiral is a thing that has a fixed window, by default 60 seconds. So you collect only 60 seconds of value. Histograms do something similar. So a reporter, there are a set of built-in reporters, Graphite, TTY if you want to print something out while testing, StatsD. In this particular case, we're setting up the StatsD reporter, and what it's going to do is refer to the thing by name. So on the previous slides, we start naming the output of Airline Statistics, Erlang GC, and we had total call and received word, and those now become metric names. And what we're saying is to the StatsD reporter, take these metrics and ship them over the network to the local StatsD daemon and report them as a histogram. So if you don't know StatsD, StatsD also has its own set of aggregate materials. Some FAR reporters don't, they just have ship it as it is. Ship it as it is often actually what you want, because you don't have as much control in the FAR reporter, so say StatsD, as you actually have an Exometer. So here where we have Buddha freak cap, or frequency cap, I should say. Buddha is the name of the system that I work on, and we have a frequency cap. So a frequency cap is the cap at which we show you an ad. So if we happen to decide one day that you really like bubblegum, we'll only show you a bubblegum ad 10 times if the customer wants it. So you can sort of violate a frequency cap, so we actually check how often we do that, and that's what this metric reports. But because that metric is so important, we don't want StatsD modifying it for us. So we want our system to be the source of truth, and we ship it across the network as a gauge, which just basically says to StatsD, don't do anything with this, just ship it across the network. And you'll find that you create a lot of gauges. And the subscription, if you'll recall, is just the regular period on which you poll. And all we're saying here is, hey, Erlang Exometer StatsD, look at this thing and report on it every second. And again, you refer to things by name and you ship them out over the network on a regular period. So it's a little goofy maybe to get started, but it's super valuable. The other thing that you have to know is Exometer, if you don't want to ship all of the attributes of an entry. So if you only care about the 99th percentile of a histogram, you can do that. Or a spiral, which has 2 different attributes. One is count, which is just the total number of entries in the spiral, and then the other is 1, which is the current aggregate sum of the spiral. I don't know why it's called 1, but it is. So in this particular case, we're only shipping 1s out of the spiral, so we don't actually care about how many values are in the aggregate. And it's also possible to do that dynamically. So if you happen to log into your system and go, oops, I goofed, I just released this thing and I don't have the configuration for it, this is me setting up a good chunk of what I just showed in static configuration. Having static configuration is super valuable for team communication. It's also super valuable for having boxes that don't matter. And it's incredibly valuable to have boxes that don't matter because you can just destroy them. The really brilliant thing is that all of these are loosely coupled at runtime. So if I decide at runtime that this histogram now needs to report to a new system, I just set it up. There's no single pipeline that combines them all in one shot so that you have to duplicate. And that's incredibly valuable when you have these high transaction systems because you need to minimize the amount of information that you're storing that isn't directly related to servicing transactions, because actually instrumenting your system is a cost. It doesn't help you in the moment serve traffic. It helps you in the long term serve traffic. And we're all in the business of building long-term systems. We're all at an airline conference. And the configuration is static, but you can adapt it on the fly. And that's very valuable to do. I mean, we've all logged into running airline systems and debugged it, and this is basically the same thing. So the reporters are the things that pick up entries and move them over the network. It's actually incredibly easy to create your own. The StatsD reporter is something that I contributed to Exometer in an afternoon, just because I needed it. It's very, very clear how to do it, and that's pretty great because you'll find that you want proprietary reporters for your own internal data pipeline, and you just throw them one in, and you refer to reporters by their module name. So Airline or Exometer will search for that particular module, and it just has to obey a certain callback. And the upstream authors are incredibly responsive to issues. I can't stress enough how important that is. So Exometer, but why not say Folsom, which is common and used by Basho? Why not Statsman or VMstat? So Folsom doesn't have the decoupling that I find so important. It's incredibly important to have everything decoupled. At the time where I experimented with Folsom, I also found it much slower than Exometer. The counters are fast because it does a particular etch trick, which I've talked to some of you about, but the other aggregate types were not as fast at the time, and I understand that they've changed that subsequently. Statman is also not completely decoupled, and it's very difficult to add new reporters into Statman. I figured out how to do it, but it took 3 or 4 days, and it wasn't as convenient as I hoped it would be. And VMstat is mostly just shake and bake. If VMstat does what you want, that's what VMstat does, but it's not extensible. You can't add new things, new entries, new reporters, anything like that, which is not incredibly valuable because as soon as you start adding more instrumentation to the system, you gain more insight into the running system, and you think, oh, well, I actually need this now, and if you can't add that, you can't gain more insight into the system. So we have this instrumentation, and we've spent all this time and money, so great, now what do we do with it? We monitor, and unfortunately, this is actually the hard part of this sort of work. So monitoring is basically 3 separate subfields of computer science all crammed together. You have visualization, turning a stream of abstract data into a pretty graph that our visual cortex can parse and allow us to make decisions on. You have alerting, which is to say, all of these pretty graphs are doing this thing, and this is actually a bad thing, so do something about it, human, please. And then you have analysis, which is deciding that all of these alerts are actually valuable, and you can do something about it. So visualization tells you how things look, but not why. So that sure looks bad, but what's actually going on? So a great example of this from our system is periodic bid timeouts. So I said we had a hard limit or a firm limit of 100 milliseconds, right? So this is a measure of how often our system is actually timing out, a measure of how often it's failing to meet that time limit. And it's spiky, which is really odd. So we decided to look at system load, and system load is not spiky. So something goofy is going on if system load is spiky, or not spiky, but our timeouts are spiky. So we started looking at various things, you know, what's going on? Does the system have a periodic task that kicks on in the VM? No, it did not. But it is correlated with network traffic. So we noticed that network traffic going out was correlated with the spike. So somewhere in the system we were creating traffic out, and that was causing the VM to spike, which is odd because the VM was not adding more traffic out on the network. And then we looked at the run queue, and the run queue was also correlated with spikes. So it means that the VM was actually backing up. Somewhere processes were being told to wait on the scheduler threads. So we have this clear idea that the system, the computer as a whole, sending more network traffic out, the VM is backing up because it's not able to process the request, and the run queues are climbing. So what happened? It turns out that the scheduler threads were locked to CPUs. So you can set that in the VM, and we had a box with 16 CPUs, but we had a background process that comes on every 20 minutes, which is the exact period of that spike, and it consumed a lot of CPU time. It was gzipping logs, basically, that we shipped to data science. And we had no CPU shield set up on the box. So the VM was allocated 16 processors, and the Linux kernel would say, hey, I have this high priority CPU task, boop, get off. So one of the scheduler threads would be knocked off of its CPU, and all of the tasks that had been allocated to that CPU would now back up. Which is bad because we want the system to not back up. We have this firm time limit. So we just allocated 14 processors to the VM, and we kept on running. So now we have 2 processors that are capable of servicing traffic for background processes, and 14 for actual customer traffic. We actually kicked the kernel off just to see what would happen, and it was terrible. Don't kick the kernel out. It makes context switching incredibly expensive. Alerting tells you that something happened, but not why. So you get this alert that says, a thing is broken, but you don't have any insight into why that is the case. So this is a graph of our traffic. And this is a normal day. This is a good day. So humans go to sleep, traffic dips, humans wake up, they surf the internet. It actually peaks around 11 in the United States, so a lot of people surf Facebook at work. So this is a normal day. This is us making money, and it's great. This is a bad day. So in particular, if you look at that cliff of doom there, that means we're no longer making money because we no longer have requests and we can no longer bid on them. If you zoom in a bit, you actually see that it's some incredible cliff. It's not that we goofed and we're being throttled by the exchange. It's actually that something terrible has gone wrong. So we started looking around, and our timeouts look good. Our timeouts look so good, in fact, that when the cliff happens, our timeouts drop to 0. And we track the number of error messages that go through Logger. And the errors look okay too. In fact, they look so good that they drop when our traffic drops to 0. There's a peak afterward, and we never really investigated it. It's sitting in Jira. Probably it's just a bunch of things coming on and saying, hey, I haven't seen this much traffic in a while. What's going on? But it was a non-fatal thing, so there was no alert for it. So what happened here? So we actually spent 4 engineers spent an hour digging into this and going, oh crap, I don't know what's going on, we're screwed. And then one of our project managers on another team turned to us and they said, hey guys, you know Facebook is down, right? None of us use Facebook. We didn't know. So we had an alert come on and everything is burning, but that alert doesn't also say everything is burning because everything is burning at Facebook. So analysis gives you why, but only if you know how to ask for what. So we track obsessively, we track the memory usage of a bidder. And this is the memory usage of a bidder over a several week period, so you see the up and down because humans go up and down, so the bidder memory allocation goes up and down. So this is normal. This is not normal. So every so often we deploy a system that we think is pretty high risk, and we let it run for quite a while. And in this case, we found that the allocation of memory in the purple line bidder there kept climbing. You see that it drops off on the far right-hand side. It drops off because it killed itself. So this is really bad. So we started breaking this down. It's not in ETS tables. We allocate a lot of ETS memory. It's actually all in binaries. So somewhere we have something allocating binary memory, and then not freeing it. So we start looking at the usual culprits. Is it processes? No, it's not processes. So purple line is the system that kills itself, blue line is a normal good system. Okay, is it an ETS? Because we have gigabytes worth of binaries in ETS. Nope. In fact, they track almost perfectly. So that subsystem is unchanged. And unfortunately, these are the 2 culprits. So a big head scratch, like where could all of this have actually gone? What happened? So Miriam Pena, my coworker, spent almost 3 weeks tracking this down, and she had this brilliant idea to make a few hundred releases that bisected all of the code possibilities. Being in the cloud is nice. It turns out it was a Jiffy bug. So a byte here, a byte there, eventually you're talking real memory. So Jiffy had this bug where it would lose a byte of binary memory every so often. And it turns out when you're doing 90 billion transactions a day, a byte every so often adds up real fast. 6 days. So, okay, great. We have monitoring and we have instrumentation. Now all of our problems are solved, right? Like we're able to understand these complex systems and we're able to just keep jamming along. That's not quite true, unfortunately. So instrumentation makes up for our lack of insight into the world around us, and while monitoring makes up for our frailty as humans, because we can't be awake all the time looking at our instruments, no solution is perfect. So nothing will quite solve every problem. So your instruments may be misleading. Your instruments might be telling you the wrong thing. They might say that the value of a certain important metric is 1, when in fact in reality it's 10, just because you introduced a bug in the thing that reports into that. We did have a production issue once where our spend, which is a key metric of the system, dropped to 0. It turned out the bidder was actually spending money. We just stopped pumping that value into Exometer. So it dropped to 0 and then all the alarms went off. But it was our fault, not the bidder. The instruments may be overwhelming, so you might actually have too much information coming out. You might have alarms going off all the time that say, system status normal, and you get instrumentation blindness. You might not look at it anymore. So your instruments may be inaccurate. So even if it's not totally wrong, or if it's not totally misleading, it might not be quite right. So if you're doing a certain statistical measure that has an error margin, and the actual value you need can be completely ablated by that error margin, but you're not aware of that value of that aggregate, you're in for a bad time. So you kind of have to understand statistics really well when you do this. And instrumentation may be ignored. You might have the perfect regime for figuring out the behavior of your system, but you might just have people on duty that don't care. They might be playing World of Warcraft, which happens. So what can you do about this? Well, a little paranoia never hurt anyone. If you think real hard about every alarm that goes off and says, is this actually the behavior of the system, especially if it violates your implicit understanding of it, you might actually find a bug in how you report. So don't necessarily take every alarm as the source of truth. Use glass displays. So every one of your engineers is going to have a vastly different understanding of how the system works. And that's okay. Everyone has an implicit mental bias for how they understand things. And when you build dashboards out of your instruments, don't force everyone into the same dashboard, because it'll violate all of your implicit biases. Just let everyone jam on their own thing. Train. Rerun disasters if you can, especially for new people. Have them go through and try and figure out what happened from historical data, which implies that you're keeping this data. Keep sight of the main goal. So our bidding system exists to serve you ads. If we get real excited about serving ads in 1/10 of a second, that violates what we're really trying to do, which is bid well, so that the ads that you see are actually valuable to you. So sometimes we take longer. We actually hurt performance because it increases the value add. And even though it's more exciting to be like, I made this thing so incredibly fast, no one cares. No one cares, so long as it serves its main goal. And recognize that even simple systems can go wrong. So every system has within it the seeds of its own destruction, and something that looks like it's so simple that it could never fail will inevitably fail on you. And if you aren't prepared to deal with that, you'll be blind when you're diagnosing issues. You'll just go, oh, okay, yeah, fine. That could never fail, and then it's that thing. And finally, if you can manage it, have resources that you're willing to sacrifice. It's incredibly valuable to be able to say, oh yeah, 10 computers just failed and I don't know why. That's okay if you have an extra 10 computers. You can't always do that, but sometimes you can. And Kirk never dies. He's the important one. Thanks. It's my understanding we have time for one question. Who's the lucky... Oh, yes.
How are you setting up alarms to analyze histograms? So if you have regular spikes of traffic every day, for example, you don't bother that, for example, you have just 50% of users in night.
Yeah.
How do you detect that there is something really unusual happening?
Yeah.
Can you repeat the question?
Yeah, so the question was, how do we set up alarms, especially when there's spiky behavior in the various time series? We found that for our particular team, the most valuable thing is to set caps, to just say that anything above this value is erroneous, so we need to investigate it. There are some sophisticated products, and increasingly we're getting data science inside of Adroll on board with this, where they will do recommendations on, well, this spike looks fishy, but these spikes look fine. And I don't understand how that would work, but mathematicians are magicians. But I particularly like the flat cap. Anything above this is erroneous because it's very easy to understand and it's very easy to communicate to new team members. And recommendations of this spike is fishy concern me. Because I like simple things, brutally simple things. And recommendation engines are not.
All right, thank you.